To get answers to questions we have, we could send out a survey and get data. We could design an experiment, or we could design a simulation. So that's what we're going to talk about here. Now, designing simulations is often computer-based stuff, but what we'll do is use a table form, which will limit the amount of calculator use that we'll have. And then in another video, we'll do a full computer or calculator program that will be the simulation. What we're going to be doing is revisiting probability a little bit. So here's a classic probability question. If a test or a set of 10 coins is flipped, what is the probability of seeing 3 heads? So far, we have actually 2 methods of approaching this question. Method 1 is to create or use, if you already have it, a theoretical model, which we did for this. This is the binomial equation. And you can plug in the numbers and get your answer. And the probability of seeing 3 heads out of 10 coins is about 11.7%. The next method, method 2, get out a set of 10 coins and flip them a whole bunch of times. This is called the empirical method, which of course is long and tedious. You wouldn't want to do that. But if it was a more complicated situation and we couldn't actually create a theoretical model, we might have to do this. Or we could do method number 3, which we're going to talk about now, simulation, in which we create a simulation of it using some kind of random number generator, and we do it a whole bunch of times, so it's like empirical, only we don't actually have physical coins, it's simulated coins. We're going to use a 5-step procedure whenever we're doing a simulation. The first one is you want to state clearly the problem or describe the experiment. Number 2, we want to state assumptions. Number 3, we want to explain the details of the simulation. Number 4, run the simulation many times. Show the repetitions or the program if it's a programmed simulation. And finally, number 5, clearly state your conclusions based on the results of the simulation. Well, now we'll go through an example. Our example reads like this. Jack lives in a dorm with 24 other people, so there are 25 people total. He decides to start a rumor by telling one person. Every person thereafter who knows the rumor, including Jack, will tell one randomly selected person each day. If anyone tells the rumor to someone who already knows it, they're so embarrassed that they stop spreading the rumor. So there are a couple of questions that this brings. How long will it take for everyone in the dorm to know the rumor? And will everyone eventually know it? Or will the rumor die out with some people having never heard it? Well, it's kind of a complicated scenario. It's going to be really difficult to create a theoretical model for this. An empirical model, well, I guess we could get 25 people and do it. That seems like it would take a really long time. Or we could simulate it. So this has been step 1. If you remember our steps, state the problem, describe the experiment. All right, so here's the problem. All right, step 2, all right, we need to state our assumptions. Each person will randomly select a person to tell. Truly random, again, humans don't do random very well, but it's an assumption we're making that they are going to randomly choose someone, regardless of whether that person knows it already or not, or even whether they've told that person before or not. I guess they have some bad memory issues going on. Step 3, whoops, went too far. Explain the details of the simulation. All right, this is where it gets pretty important and you start working out the details. To start with, in my simulation, I'm going to use the number 1 to represent people knowing the rumor. A blank is going to represent not knowing the rumor. So every person is going to have either a 1 or a blank. Or they might have an X. If they tell someone who already knows, they're going to stop spreading it. So I'll put an X by that person because they're not going to spread the rumor anymore. I'm going to assign every person a number, 1 to 25. I think I'll make Jack number 1. And each day will be simulated by using the randint function in my calculator to determine who each person will tell. So here's some details. What's already in my mind is I'm seeing a big table of people's 1 through 4 and days going down, something like this. So here are my 25 people, and this is day 1. So looks like on day 1, only Jack knows. So he's got a 1, everyone else is blank. Now we need a randint to figure out who Jack's going to tell. So I come over to my TI-84, I go to my math, and probability, and number 5 is randint. Now, I shouldn't actually enter 1 to 25 because Jack's not going to tell himself. There's 24 people that Jack can tell. So he's going to tell the 8th person. Now, we have to be a little bit careful here because, of course, this 8, in fact, doesn't refer to this 8. Because if the 24th person was, came up here, then, well, what about the 25th person? I mean, clearly, if we start from here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 24. Really, those are the 24 other people that he's going to tell. So when this randint function shows me an 8, it's going to be 1, 2, 3, 4, 6, 7, 8 is actually going to be here. So what I'm going to do is put a 1. Oh, wait, this is day 2. So now this person knows, and Jack knows. And I'll just show you how I want you to show the randint. So off to the side, I have my randint with the results. And day 2, 2 people know. Right? Day 3, Jack's going to tell someone, and this person number 9 is going to tell someone. So I have to figure out who they're going to tell. And I'm going to use randint 1 to 24, and I want 2 numbers. So I run the function and get 20 and 9. So this is going to start getting a little bit more complicated. I have to actually say, all right, well, Jack is going to tell the 20th person, and this person's going to tell the 9th person. Because again, we have to be a little bit careful about, the skipping. So if this is really, from Jack's perspective, person 1, 2, 3, 4, 5, right? 20th person is going to be this person, down here. So that's who Jack tells. Now this person tells the 9th person. Well, from this person's perspective, here are 8 people, so the 9th person is actually that person. And then, of course, they still know. The next day is simulated. This person tells person number 1. This person tells person number 10. this tells person number 7, and this tells person number 8, which means this person, Jack, person number 1 from Jack's perspective is there. Person number 10, now this is kind of interesting, is of course 8, 9, 10 is this person. This person tells number 7, which would be that person. And, let's see, this person tells person number 8, which from their perspective would be that person. And, of course, all these people still know themselves. So, we're up to, 5, 6, 7, 8 people knowing the rumor. Let's simulate the next day. Those are the numbers I get, and I'll write them beneath the people telling them, like that. So Jack's going to tell the 16th person from him, which is actually going to be person 17. Cool. This person's going to tell the 16th person, which is really actually going to be the same person, right? Because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is actually 16 is the 16th person. It's the same person. They already know. So I would say this person just told someone who already knows, which means they're done. This person is telling person 14, which would end up being this person. This person is telling 17, which is in fact that person. This person's telling 5, which would be that person. 20, which would be this person. They already know, so this person has stopped telling people. And this is person number 8, which of course would be this person. Well, they already know, so that person is now stopping. This is telling person number 12, right, which means they know, and of course they know, they know, they know, they know, and Jack knows, of course. And so all these people know the rumor. Next day. Notice for a moment that I'm using 10. There are actually 13 people who know the rumor, but 3 are no longer telling the rumor. So it's just 10 people who are spreading it. All right, Jack's telling person number 10, who is this person, already knows. So Jack is stopped, and these people have all stopped. So Jack is stopped. Now this is, what number is that? 18, which is going to be this person. Oh. They just told someone who already knows. 15 is this person. All right, now this person knows, and that person told them. This is 16, which is going to be, that person. So they stopped telling them. Tells person 17, which is that person. They've stopped telling people. This person's telling number 9, who is that person. They're stopped. Number 10, they're telling number 10, who already knows. So they're stopping. They're telling person 13, who doesn't know. Right? So now person 13 knows. This person's also telling person 13, who was already told. So now they stop telling. This is person number 14. Right? Number 14 now knows, and of course, they still know. So all of a sudden, we only have 1, 2, 3, 4, 5 people spreading the rumor. Everyone else knows it, but has stopped spreading it. The next day, this person wants to tell person number 20, who is in fact this person, already knows. This is telling person 13, who would actually be this person. They already know. 17 would be this person. They already know. They're going to tell person 21, who would be this person. This person now knows. And they know. And this person tells person number 3, who, now knows. So that's good. And then these people know, but aren't spreading. And there are 4 people still spreading the rumor. Here's the next day, telling person number 9, who is this person, already knows. Telling person number 20, who is that person, they already know. This person is telling 17, who is that person? 17 now knows. Right, and this person is person 20, right, who now knows. Right, so there's still 4, and these people are all in the know but not spreading. Here's the next day, telling person 16, already knows, so they're done. Tells person number 18, already knows, so they're done. Tells person 1, Jack, who already knows, he started it. And person number 21, who is that person, and they already know. So all these people have told someone who already knows, so they have stopped spreading the rumor. And is there anyone left to spread the rumor? No. So at this point, the rumor dies. Does everyone know? No, there's actually 1, 2, 3, 4, 5, 6, 7 never heard. And the rumor died after 9 days. So you can see it's a little complicated. It'd be hard to get a theoretical equation for this. We do a simulation, and we get our answers. Now, of course, if we do the simulation again, would we get the same numbers? Right? Again, we're dealing with, random, we're dealing with some probability. The answer's no. We wouldn't get the same numbers. So what we want to do, and this is, of course, hold on, there we go. We want to run the simulation many times so that we can kind of get an average. We can start doing some statistics on that. And this is where, boy, it would be really nice if we could automate this part of it. And that's where programming comes in, where we could actually write a computer program or a calculator program that would do all this for us and get the results, and we could just run the program a bunch of times. Because although this is certainly much faster than actually trying to spread the rumor and waiting, 9 days or so, and then having to do it over again, that would take even longer. Still, this was kind of a pain. Doable, but if we know how to program, it gets that much easier. I ran the program a bunch of times, and here are my results. So, let's see, 5 by 6. I ran it 30 times, and here are the number of days it took for the rumor to die. And here's the number of people who never heard. And of course, we can find some statistics on these. So it seems it takes an average of about 9 days for the rumor to die. And on average, 6 or 7 people will end up not knowing. Actually, only one time did everyone know. And there was one time that almost no one knew. Only 2 people. That's a very unusual occurrence. But hey, you know what happens. So, there's the simulation. Now that I've finished, I should go back and let you guys know that, I just made it look like, oh, I knew exactly how to do this. It actually probably took me about, 3 trials for getting this table right. Like, what information did I need and, to write these little subscripts and to kind of keep things organized. It took me, I think, 3 tries to get the system that would work. So, you're going to have to try it, trial and error, see what works. Is this the only way to set up this particular question? No, I'm sure there's probably better ways of doing it. This is just kind of what first came to my mind. So there's lots of ways of doing it, and you can come up with your own design for your simulation. Oh, and I almost forgot. We have, oops, wait a minute. There it is. We ran the simulation. We actually haven't clearly stated our conclusions. We need to do that. So here it is, the conclusion. For 29 out of 30 trials, the rumor died before everyone had heard it. Therefore, I would expect the rumor to die before everyone has heard it 97% of the time, after an average of 9 days, with an average of 7 people having never heard the rumor. There's